So as I've tried to make a point of, quantum mechanics was built on several different scientists' work, not just like one, but notably Schrodinger and Heisenberg. They worked on something that led to wave functions, and wave functions are what we use in chemistry to describe where electrons live. Like, that's the easiest way to put it. Think of wave functions giving us information about orbitals, which is just where electrons live. So wave functions are what we use to determine the distribution of the electron's density with respect to the nucleus. So it's the math behind determining where an electron most likely will be. And what we call that area of where it will be, the electron density, is orbitals. So atomic orbitals, they are where you will most likely find a certain electron in 3D space. This diagram right here shows you a bunch of different orbitals, but we're going to break it down step by step. So far what we've learned about electrons, if you watch the video on the Bohr model of the atom, you learn that electrons live in certain levels of energy, right? And these are discrete energy levels, meaning that they don't live in between, like they don't live in 1.5 level. They live within either 1, 2, 3, just whole numbers, right? So we know that so far, but we are going to learn about how electrons have very specific addresses. So these addresses, and they're actually quantum numbers, tell us a lot of information about the orbitals that electrons are in. So anytime you hear quantum numbers, just think the address of the electron. Don't freak out. I know quantum number, like it just sounds intimidating, but it's the address of the electron. So we're going to learn about these 4 numbers. So our first quantum number is called the principal quantum number, and we denote it with a lowercase n. And I have an analogy system that hopefully helps you remember what these numbers mean. And n is our first number, so it's our most like bird's eye view of the house that the electron lives in. So it tells us the address of the actual house the electron is in. It doesn't tell us anything about which room it's in, about which level of the house it's in. It just tells us the house number. So very like bird's eye view, think of it that way. What it actually tells you in real life about the electron, the energy level of the electron, so you can see here as n increases, then our shell is getting bigger and bigger, and that's another name that we call this number, is a shell. What you need to know about it is that the bigger the number, the further away from the nucleus, the higher the energy level. And then our range begins at 1, and theoretically it can go on till infinity, but we stop around 7 for our periodic table, the atoms that we have. And you can calculate the total number of orbitals in a certain shell by just squaring the n value. Our next quantum number is our angular momentum quantum number. We denote it with a L. So sometimes you'll see, and it's like italic L, so sometimes you'll see this like a cursive L, or sometimes you'll just see the italic regular L. Now the analogy for this is it's the house level, and each level has a certain type of room on that level. So here you see house number 4, for example. Remember, that's our n value. This house has a total 4 levels. So here you can see house level 0, house level 1, house level 2, house level 3. Now, keep that in mind, but let's talk about what this actually is. So it tells you the shape of the orbital, and we also call that the subshell of where the electron is in. So these are the different shapes. So here we have s orbitals, p orbitals, and d orbitals, right? And we actually have another type of orbital called f orbitals. I don't have them right here, but we will talk about them later. Now what you need to know is that each value, so each of these shapes has a certain value that corresponds to it. Each value corresponds to a certain shape and name of the orbital, right? So this has a sphere shape, this has a dumbbell shape, this is like 2 dumbbells, and then the F are just more complicated. So that's what you need to know. There's a certain value, it has a shape and a name. So the range starts off at 0. The max the max L value you can have for a certain N value is N minus 1. So here you can see this is house number 4, right? N equals 4. The max L value you will have in that house is L equals 3, so 4 minus 1. And then again, each L value, so L equals 0, corresponds to S orbitals, which are sphere-shaped. L equals 1 corresponds to p orbitals, which are dumbbell-shaped. And L equals 2 corresponds to d orbitals, which are like 2 dumbbells. For the most part, you're only going to need to know the shapes of SP and D. That's what I mean by we'll only worry about SP and D. But you do need to know about F orbitals and what L value that is. And that is L equals 3 for F orbitals, okay? But for the shapes, don't worry about it. Like, they're really complicated. So the next quantum number is the magnetic quantum number. We denote this with an M and then a subscript L. Sometimes you'll see it like this with the cursive L. Now with this, how I relate this to the analogy is that this tells us your room number. Now, what we have learned so far is that we have an N quantum number, the principal quantum number. This is like our house number, right? And then we have our L values, which are our magnetic quantum numbers, and they correspond to different types of orbitals that we have within this house, right, within this energy level. So we have L values that correspond to certain shapes, certain names of orbitals. Now, each of these levels have a certain amount of rooms within them. So you can see here, for example, house level 0 only has 1 room, and we're counting the rooms as squares, right? It only has 1 room. How do we explain that? Now, this has to do with the orientation of the orbital. So magnetic quantum number tells us the orientation of the orbital. So each value corresponds to a certain orientation. Now, look at the s orbitals. They're a perfect sphere. So if you turn it around this way, turn it around this way, turn it around whichever way you want, it's going to be the exact same thing. Think of like one of those like play balls that are really like bouncy that children play with, and it's like one solid color. You just turn it around, same exact thing. Turn it around, it's going to be the same no matter which way you orient it. Now, every other orbital does have certain orientation. So for example, the p orbitals, there are 3 axes in 3D space, right? On paper, for example, when you're in like college algebra, you learn about the x and the y axis, right? But in actual 3D space, you have 3 dimensions. That's what it stands for. You have the x, right? Let's say this is the x, and then this is the y, and then this is the z. So you have 3 different types of axes, so you're going to have 3 different types of orientations for the p orbitals. So they'll be on each different axis. Now the d orbitals, they're kind of a little bit more complicated. You have those different combinations of axes, and then you have this weird d orbital that's a dumbbell with like a donut around it. Don't worry about knowing the actual like axes that each one is in. Just know that how many orbitals are within each level. So within L equals 0, there is only 1 orbital, 1 orientation. When within L equals 1, which corresponds to p orbitals, there are 3 different orientations, right? 3 different rooms. Within L equals 2, there are 5 different orientations, right? 5 rooms. And then for F orbitals, there's 7. So the range is between negative L to positive L. Now, let me explain what this means. So let's say we're looking at L equals 1, right? And we want to figure out how many orbitals, how many rooms there are within this level. So what the magnetic quantum numbers can be, right? The magnetic quantum numbers that are within L equals 1, you will start off at negative L. L is 1, so negative 1. You go 0, and then you keep going until you get to positive L. So now that you wrote those out, you can actually go back and say, okay, how many different ml values do I have here? I have 1, 2, 3. Same thing that you have right here within our little house. So the house analogy, again, it's just for you to kind of be able to kind of put these two together, and it kind of gets you used to how many orbitals there are within, the fact that each quantum number is kind of zooming in more and more into where the electron lives. So that's what each quantum number does. First, you're like, okay, the house number, then, okay, within a certain level, and then you learn about this one, and then you're like, okay, within a certain room. So you keep zooming in into where an electron can live. So we're going to talk a little bit more about each orbital. So first we have our s orbitals. The s orbital looks like that. It's a sphere. It only has one possible orientation, so that's why you only ever have one ml value for it. It's spherical. It's centered on the nucleus of the atom, and this is just in general that the shapes of orbitals are where the electron has greater than 99% chance of being, and that comes from all the math from wave functions, but you don't have to know that. You just have to know the shapes, the quantum numbers, what they're called, and so on. So next we have the p orbitals. They are dumbbell shaped. This is how they're arranged on or oriented on the different axes. And remember, we can only start having p orbitals once n equals 2, because remember, the maximum value for L is n minus 1. So you cannot have p orbitals within n equals 1. Why? Because the maximum number for L when n equals 1 is 0, and that's the only one. So within the first energy level, you do not have any p orbitals. They start at n equals 2. So they're arranged on the different axes. You have 3 different p orbitals. They're the same size. We denote them as px, py, pz for the different axes, but do note that this does not equal, okay, px corresponds to ml equals -1, py corresponds to 0, and so on. It does not mean that that one corresponds to each one. There's a whole lot of math behind that you don't have to know, but just know that they don't necessarily like correlate with each other. Next we have the d orbitals. The d orbitals are a clover shape. So you can see here, for example, that for the most part we call them like a little clover or 2 dumbbells, however you want to think about it. And then there is that one that's weird with like 1 dumbbell and like a donut around it. D orbitals begin in the 3rd energy level, so in the 3rd shell, and this is the possible range for them when you look at the ml values, and these are the different like notations for each specific d orbital. So there's a total of 5. Remember, when we look at the rooms, there's a total of 5, and you can see here there's 1, 2, 3, 4. There should be another one. I don't exactly know what it is, but there should be another one. And you can tell again from, sorry about that, you can tell again from the ml values. You have 1, 2, 3, 4, 5. So next is our f orbitals. We are not going to talk much about their shape. They're weird and complicated, that's all you have to know. But do know that they correspond to L equals 3, and there's a total of 7 of them. So 1, 2, 3, 4, 5, 6, 7. If you count them here, 1, 2, 3, 4, 5, 6, 7. And here again, in our analogy, if you count up the total number of rooms within the house level 3, then you're going to find that there's 7 of them. But do know the shapes for S, P, and D. And finally, we have the spin quantum number, which we denote with M and then subscript S. You can think of this as the bunk bed within the room that the orbital is in. So you have a total of 2 bunks within, right? Just a regular bunk bed with a top and a bottom. So in terms of how this relates to the quantum number is that it tells you the spin of the electron within that orbital. Only 2 electrons can fit within an orbital. So any orbital, whatever it is, if it's a 3f, if it's a 2p, if it's a 4f, a 3d, it doesn't matter what it is. Any orbital can only fit 2 electrons maximum. And that's because it only has a bunk bed. So how are you going to fit more people in there if you only have 2 beds, right? Again, so this is what it overall tells you, that only 2 electrons can reside within one orbital. Now the actual values that we have that correspond to the ms, the spin quantum number, it's either -1/2 or +1/2. This corresponds to the spin of the electron. So it can either spin up or it can spin down. So we consider like the +1/2 as spinning up, and then the -1/2 as spinning down. So here you can see that I actually placed electrons within each room, and you can see that one has a spin up, so +1/2, and one has a spin down, so a -1/2. And you can actually go ahead and count all the electrons that are within this house that live within this shell, this energy level. But you can calculate it, you can count it if you want, or you can calculate it using 2n squared. So let's say you want to figure out how many total electrons reside within n equals 4. So you would take 2 and then 4, square it. So 2 times 16, that gives you 32. Now I do want to point out something that may be like interesting or something that may be confusing. Why are atoms spherical? Why are we always drawing them as a sphere if they actually have these weird shapes within them of where the electrons are, right? And that's because overall, the way that it adds up is that you will have increasing energy levels, and because of that, the distribution overall adds up to kind of it just being a sphere. So these are some good summary tables that kind of condense everything that we just talked about into these like little short and sweet tables. So for example, this one tells you the quantum numbers, their properties, significance. So the symbols, the names, the values. I think this one is very important because what trips a lot of students up is the possible L values and the possible ML values for a certain quantum set. And then it tells you the actual physical meaning. And then I have my little analogy thing right next to them so that you kind of put them together. I like this table because it shows you all the different ML values. It tells you the number of orbitals within a certain L value, so within a certain level of the house. So notice that this makes up that shape of the house because that's essentially what it's showing you. So these are the different little houses. And then again, remember another major thing is that the number of electrons per orbital is always 2, regardless of any type of different orbital. So finally, here we have some different examples of questions that I can ask you. So I can test you on quantum numbers in many, many different ways, and you'll see that once we answer these. So first question, how many orbitals occupy L equals 2? Now, the reason I like to give this little house analogy is because you can use it, and if you have it like drawn out or printed out, then you can just use it as your little cheat sheet along with these labels. So let's say you're looking for how many orbitals occupy L equals 2. All you have to do is go to your second house level, so L equals 2. Circle it off for yourself, whatever you need to do, and then you count, and if you know the analogy, then you know that the orbitals correspond to the rooms, and the rooms are the little squares. So 1, 2, 3, 4, 5. Another way that you can do this, if you don't want to necessarily just rely on this like house analogy, is you should know that the way that you get the number of orbitals within a certain level is that you determine your ML values. So for L equals 2, your ML values are, they range from -L to, keep going until you get to +L. So for ML here, and sorry, this looks horrible, it looks like ME, should be like that, ML, subscript L. You start off with -2, you keep going like down the number line until you get to +2. Now what you do is you count off how many numbers you found. 1, 2, 3, 4, 5. So whichever way you want to do it. So that one's done. Next we have how many total electrons are within n equals 3. So if you recall, we learned that you can calculate total electrons by just a simple equation, which is 2n squared. So for this one, it's right here. And we're just going to plug this in. So 3 square it. Actually should have written that right there. So let's erase that. So let's solve this out. So 3 squared is 9, so 2 times 9 equals 18. So that would be our answer for the second question. And then finally, and if you actually wanted to do that, you could square off your n equals 3. If you draw n equals 4, you're pretty much good for the almost everything else. So n equals 3 would have one level less, and if you counted out all the electrons within what I just blocked off, it would be 18. So whichever way you want to do it. And then finally, how many electrons can reside in the following set of quantum numbers? So we have n equals 2. So again, we can block off if we need to, right? We can use that same house, but we block it off. So n equals 2 has 2 possible levels, right? And specifically, we're looking at L equals 1. So we're looking at this level, right? So remember, address gets more specific as you go down the quantum numbers. And then ML equals 0. So specifically, we're just looking at one of the 3 rooms. Let's say this one is 0. Like that's the label outside of the room. So we're just looking at one orbital, that's all. And one orbital can fit 2 electrons. So there's kind of different ways you can use our little analogy. You can, if you know how the quantum numbers and the ranges work and what they mean, you can do that. It's up to you. But these are several different examples of how I can ask and test your knowledge about quantum numbers.